Hi, my name is Aneta and this is Chemistry at Glance. In today's video, we're going to practice some past paper questions on forces between molecules, hydrogen bonding and shapes of molecules. If you're not familiar with this topic, as always, I'll leave all the links in the description box below for my blog and a post on these topics, so go ahead, read through them. They're all very easy to read and they are short and concise, so I hope you'll take away a lot reading these. So, our first question: when the temperature is increased, both solid iodine and diamond change directly into their gaseous state, they sublime. In each case, name the force or bond that is being overcome when a solid changes into gas. So in iodine, although I2 is a covalent bond, all the I2 molecules are joined using only van der Waals, which are weak forces. So the force that has to be overcome in iodine is van der Waals. In diamond, you have carbons bonded covalently with each other, so covalent bond has to be overcome. And next question says, state with a reason which solid would have a higher sublimation temperature. These are the forces, and as I told you, van der Waals are very weak, and they're definitely weaker than covalent bonds. Therefore, diamond have a higher melting temperature because covalent bonds are stronger. This is the order. The intramolecular forces, so the covalent bonds, ionic bonds, are bigger than hydrogen bonding, and then hydrogen bonding is bigger than van der Waals. So van der Waals has the weakest forces. And that's exactly what I was just talking about, with the following in order of increasing strength. So covalent bond is the strongest because it's the intramolecular forces inside the molecules. Then hydrogen bond is the strongest. Not the strongest, but stronger than van der Waals forces. Van der Waals forces are the weakest forces. Now we have to use the VSEPR theory to deduce the shape of BF3 and NH3. So to do that, I always just draw the dot and cross diagram. Boron has 3 outer electrons, has 3 chlorines, so chlorine has 7 electrons. So that's just an ionic form, ionic bond basically, between boron and fluoride. NH3 nitrogen will bond with hydrogen, but it's still gonna have that one lone pair because it has 2, 3, 4, 5 electrons. So it still have 2 unbonded electrons. That means that we can now find the shapes of these molecules. So BF3 is boron and has fluorine, fluorine and fluorine. We always have to look at the bonded pairs and lone pairs. So it has 3 bonded pairs, so 3, and the bond angle in this one is 120 degrees. However, in NH3, we have 3 bonded pairs, so like this, plus 1 lone pair. Therefore, it's not going to be trigonoplanar anymore, it's going to be tetrahedral with 1 lone pair. If you ever wondered what this means, it just gives the shape, it's like more 3D like this. So you have 3 bonded pairs, 1 lone pair. So with 1 lone pair, the bond angle is no longer 109.5, it's going to be 107.5 because the repulsion between the bonded pair and lone pair is different than between a bonded pair and bonded pair. So the next part of this question says, boron fluoride reacts with ammonia to make the compound shown in the following equation. So this is the equation. Name the type of bond formed between N and B. So this is a boron fluoride and this is a nitrogen. As you can see, boron has no more electrons that can be used, and nitrogen still has a lone pair of electrons. This means that this lone pair of electrons can be donated to boron, basically shared with boron, but both electrons coming from one atom. Therefore, as we said before, it's a coordinate bond. Oh, we actually haven't said it before. We had it said in the previous videos. So if you haven't watched the previous videos with the questions, go on and watch it. Also, if you want a copy of these questions, I have everything in Word documents. So just email me, leave a comment, or contact me through my website. Or a blog rather. Next part says, suggest the value for the FBF bond angle in this molecule. Explain your answer to part 2. So it's going to have, boron fluoride already has 3 bonded pairs. And if it's going to bond to nitrogen now, it's going to have 4 bonded pairs. And the shape of when there are 4 bonded pair of electrons is called tetrahedron. And the explanation is basically because we're going to have 4 bonded pairs now. And the bond angles are 109.5 degrees. You have to learn this, and everything all about shapes you can find on my blog. And all the molecules have to know. So the next question says, select all the molecules from the list below that have bond angles of less than 109. So let's start with this side. NH4 plus. This means it has 4 bonded pairs, so it's going to be 109.5 degrees, no less than 109. BF3, it's going to be like this, so it has a bond angle of 120. Which is no less than 109. Na3, we also drew it right here. It had a bond angle of 107.5 degrees. Next, we have CH4. It's going to have 4 bonded pairs, no lone pairs. Because carbon is in group 4, so it's going to have 4 outer electrons, which are going to be used by these hydrogen. So it's going to have 109.5. So this one's not, this one's not, this one's not, this one is. SF6, so it's going to be an octahedron. It's going to have 6 bonds, and the bond angles in octahedron are 90 degrees. So yes. And the last one, H2O. In H2O, we're going to have oxygen with these 2 lone pairs and 2 bonded pairs by hydrogen. So, yes, because it's going to be 104 degrees with 2 lone pairs. 2 lone pairs is 104 degrees. 1 lone pair is 107.5 degrees. And if you have no lone pairs but 4 bonded pairs, it's going to be 109.5 because it's tetrahedron. Okay, so I've got more questions. The bond angles in molecules of methane and water as shown in the diagram. Use the valence shell electron pair repulsion theory, which is our VSEPR theory. State why methane has the shape shown. So basically, carbon has 4 outer electrons, and we've got 4 hydrogens bonded into it, each having 1 electron, so it's gonna be bonded covalently with that carbon. So they're gonna share these electrons. Therefore, methane has this shape because carbon has 4 outer shells, hydrogen needs 1 electron, and we have 4 of them. So no lone pairs, but just 4 bonded pairs. So it has 4 bonded pairs, therefore it's a tetrahedron with 109.5 degrees bond angle. Next one says, explain why HOH, so our water molecules, bond angle is less than the HCH bond angle in methane. So obviously, methane has 4 bonded pairs. So the shapes that are about bonded pairs and lone pairs. So we want to write like this. For example, our CH4 and H2O. So in CH4, we have 4 bonded pairs and no lone pairs. In our H2O, we have 2 bonded pairs, 2 hydrogens, but we also have 2 lone pairs. This is why the bond angle is going to be less than that in methane for water, because the repulsion between lone pairs and bonded pairs is greater than that between bonded pairs and bonded pair. As you can see, the angle here between these is smaller than this one because the repulsion between this and this is smaller than the repulsion between this and this. Our next question. The boiling temperatures of some hydrogen halides are shown in the table below. Explain in terms of the nature of the intermolecular bonding present, intermolecular, so the outside between molecules, why the boiling temperature of hydrogen iodide is higher than those of hydrogen chloride and hydrogen bromide, but is lower than that of hydrogen fluoride. So we know that the boiling temperature increases as the mass increases, because as the mass increases, the number of electrons increases. Therefore, it's harder and harder to separate them. Therefore, the boiling temperature increases. HI has a bigger mass than HBr and HCl. It also has a bigger mass than HF. However, with HF, there's something else going on. Remember hydrogen bonding? I told you that hydrogen reacts with one of these, oxygen, nitrogen, or fluoride. This is what happens here. Hydrogen bonds with fluoride by hydrogen bond. Hydrogen bond is much bigger than van der Waals, or it also overcomes the idea that boiling temperature increases as mass increases. That's why hydrogen iodide has a bigger boiling temperature than these, but not bigger than HF, because in HF we have hydrogen bonding and it's very strong to overcome. Now draw a diagram to show hydrogen bonding between 2 water molecules. So what you want to do first is draw these molecules. We know that in water molecules we have a polar covalent, because oxygen has much more control over the electrons than hydrogen due to their electronegativity. If you don't know what I'm talking about, go on to the previous video with the questions, or go and visit my blog on the previous topic and you will surely find out, because the oxygen has a bigger electronegativity value than the hydrogen. When it's took away, this means the molecule is polar. And now we have our another water molecule. Hydrogen bonding occurs between hydrogen and oxygen. So it occurs in water. And it has to occur between a more positive or slightly more positive atom and a slightly negative atom. So this is an example where the hydrogen bond could occur. And you just draw these little lines and indicate it as hydrogen bond. You could also draw another one. And you would have a hydrogen bond in here as well. But just one is fine for the exam. And the last question. Liquid water, H2O, is denser than ice. Give an explanation for this fact in terms of hydrogen bonding between the molecules. So, hydrogen bonds hold the water molecules together, as in this example. They hold it together. However, when the water is frozen, the hydrogen bond holds these water molecules apart in what is called an open crystal lattice. So how you answer this question is hydrogen bonds hold water molecules apart in ice in an open crystal lattice. And by the time when the ice is melted, the hydrogen bonds come back together, which means that water is less dense than ice. I just wanted to know, at the very end of these questions, that polar molecules will dissolve in polar molecules, and non-polar molecules will dissolve in non-polar molecules. So what this means that in water, water is polar, so only polar molecules will dissolve in this water. If we have CH4, methane, it's non-polar because the electronegativity difference is not big, and therefore only other non-polar molecules will dissolve in it. An example of this is oil and water. Water is polar, oil is non-polar. That's why we always have oil on the top of the water, not dissolving in it. So these were all the questions I had for this topic. Remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I leave all links in the description box below. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Thank you. And don't forget to like, subscribe, and see you soon. Bye.